Welcome to the new era of video creation with BioZ8. Today we will discuss design and optimize a multimodal AI system. You are designing a retrieval augmented generation RAG system for a large-scale enterprise application. How would you optimize the retrieval process and integrate it with a generative AI model to ensure fast and accurate responses? Multimodal AI systems process and integrate multiple types of data, such as text, images, and audio. Unlike unimodal models, which focus on a single data type, multimodal AI requires complex data fusion techniques to combine semantic information across different modalities. The biggest challenge is aligning different data representations. Text is sequential, images are spatial, and audio is time series data. Each modality has different pre-processing, embedding techniques, and computational requirements. Several advanced multimodal AI models exist. CLIP, contrastive learning for images and text, maps text and image embeddings into the same latent space. Flamingo, DeepMind's few-shot multimodal model, specializes in visual language tasks. GPT-4v extends LLM capabilities to vision. Whisper, OpenAI's ASR model, converts spoken language into text, aiding speech understanding. Real-world applications include AI-powered search, medical image interpretation, self-driving vehicles, and accessibility features for visually or hearing-impaired users.
Choosing the right architecture is critical for effective multimodal AI models. Transformers dominate modern AI architectures for text, e.g. BERT, GPT, images, e.g. VIT, and audio, e.g. Whisper. They handle large-scale data and enable cross-modal learning. Fusion strategies determine how modalities interact. Early fusion features are combined before model processing, e.g. concatenating embeddings. Late fusion, each modality is processed separately, then combined at the decision level. Cross-attention mechanisms allow modalities to influence each other dynamically. Embedding strategies, joint embeddings, force all modalities into a shared latent space for seamless interaction. Separate embeddings preserve unique characteristics of each modality and combine later. Pre-training versus fine-tuning, pre-trained models, e.g., CLIP, Flamingo, GPT-4v, provide a strong foundation. Fine-tuning on domain-specific datasets, e.g., medical autonomous driving, improves accuracy for specialized tasks. The right architecture and fusion strategy depends on task requirements, computational resources, and data complexity. To ensure effective cross-modal learning, optimizing representations across modalities is key. Contrastive learning, CLIP-style models, aligns text and image representations in a shared embedding space, enabling zero-shot classification and cross-modal retrieval. Multimodal attention mechanisms allow different modalities to influence each other dynamically. Cross-attention layers improve learning by allowing the model to attend to relevant features from other modalities. Masked modeling techniques enhance data representation learning. Masked image modeling, e.g. MAE, masked autoencoders, improves feature learning. Masked text modeling, e.g. BERT-style training, enhances text comprehension. Domain adaptation is essential for specialized applications. Fine-tuning pre-trained multimodal models on domain-specific datasets, e.g. medical scans, plus clinical reports, improves performance in real-world tasks. By optimizing cross-modal learning, multimodal AI achieves higher accuracy, better generalization, and improved task adaptability. Effective dataset preprocessing is foundational to successful multimodal AI systems. Each modality requires its specific preprocessing pipeline. Text data is processed via tokenization, splitting text into words or subwords, and embedding generation, e.g. Word2Vq to BERT. Images are resized, normalized, and sometimes augmented, e.g. random cropping, flipping. Audio often undergoes spectrogram conversion or MFCC extraction to convert waveform data into something more interpretable for machine learning. Data augmentation is particularly important in multimodal systems to avoid overfitting and enhance generalization. For images, techniques like rotation, cropping, and color jitter are commonly applied, while audio augmentation might involve pitch shifting or noise injection. Aligning data across modalities is essential. For example, associating image captions with images or syncing audio with corresponding text. High-quality annotations, e.g., expert-labeled image captions or transcribed audio, ensure the model has the best possible data for learning. For multimodal AI, real-time inference must balance accuracy and speed. Optimization techniques ensure that models run efficiently in production environments. Model compression techniques such as quantization, reducing precision of weights, and pruning, removing unnecessary model parameters, shrink model size while keeping performance intact. Efficient embeddings use lower dimensional vector representations of data, e.g. for images or audio, while maintaining essential semantic information. This reduces computational costs during inference. Edge AI allows models to run on-device instead of relying on the cloud, which improves latency and ensures user privacy. This is particularly useful for applications requiring instant feedback, e.g. voice assistants, autonomous driving. Asynchronous processing enables concurrent task execution, reducing waiting times. For example, batching multiple queries for text, image, and audio processing can optimize resource usage and speed up inference.
To reduce latency, it's crucial to optimize the inference pipeline. Some strategies include hardware acceleration using GPUs and TPUs provides significant speedups for both training and inference, especially when dealing with large multimodal models. Model parallelism can be employed to distribute computations across multiple GPUs or TPUs, allowing the system to handle larger models without sacrificing performance. Early exit strategies are becoming more popular. These allow the model to exit early once it is confident in the response, thus improving inference speed when certainty is reached quickly. Caching frequently requested queries, such as popular audio clips or image searches, helps avoid redundant processing. Additionally, optimizing pre-processing pipelines ensures that only necessary steps are executed. These latency reduction techniques are particularly important for applications requiring near-instantaneous feedback, such as real-time voice assistants or autonomous vehicles.
Evaluating multimodal AI systems requires both traditional metrics and domain-specific benchmarks. Accuracy, precision, and recall are standard for tasks like image classification or audio transcription. For example, in image captioning, accuracy measures how correctly the generated captions reflect the content of the image. Cross-modal consistency ensures that the results from one modality do not contradict another. For instance, if a model generates text from an image, the generated description should be consistent with the image's actual content. Human evaluation remains crucial, as multimodal tasks often require subjective interpretation, e.g., image captioning or open-ended question answering. Human ratings help assess naturalness and relevance in outputs. Finally, evaluating real-world performance using task-specific benchmarks like VQA or image captioning allows you to assess the system's capability to solve practical problems. Deploying multimodal AI systems in real-world applications poses several challenges. Data privacy and security are major concerns when dealing with sensitive multimodal data, e.g., healthcare images or personal audio. Data needs to be processed and stored with strong security measures to comply with privacy regulations like GDPR. Model drift refers to a situation where the model's performance degrades over time due to changes in the data distribution. Continuous monitoring and periodic retraining are necessary to maintain accuracy and fairness. Cross-platform compatibility is challenging as models must work seamlessly across devices, e.g., mobile devices, edge devices, and cloud infrastructure, requiring optimization for hardware-specific constraints. Scalability becomes a key concern when deploying to a large user base. It's critical to use distributed systems and cloud infrastructures to manage high query volumes and ensure responsiveness. Post-deployment, ensuring a robust monitoring pipeline is essential for a smooth multimodal AI experience. Model monitoring involves tracking the model's performance metrics, such as accuracy, latency, and user feedback. This helps identify potential problems early. A/B testing allows the evaluation of new models or system improvements by comparing them to the current model, identifying which approach performs best. Model versioning ensures smooth transitions when deploying model updates, enabling quick rollbacks if issues arise. Efficient resource allocation is crucial for handling high usage demands. Using cloud autoscaling features ensures resources are dynamically allocated as needed based on usage patterns. Designing multimodal AI systems requires addressing challenges related to data preprocessing, model optimization, and deployment efficiency. Key takeaways include cross-modal learning allows AI to tackle complex tasks that require understanding from multiple perspectives, e.g., text, image, audio. Choosing the right architecture and fusion strategy is essential to handle the unique needs of each application. Reducing latency through techniques like model compression and hardware acceleration ensures that real-time applications perform well. Continuous monitoring and testing ensure long-term reliability, scalability, and performance of multimodal systems. By following these best practices, we can build efficient, scalable, and reliable multimodal AI systems ready for real-world applications.